Fractals. My presentation is about fractals. I am Mia, and I am in the same math study class as everyone else. So, what are fractals? They are usually described as a complex, never-ending pattern of geometric shapes. They have a symmetric type of visuality, allowing the pattern to be mirrored. As we can see with this triangle, as long as you keep zooming in, it replicates. So these bigger triangle will be the same as this larger triangle, and then upon zooming in, it is the same in the smaller ones as well. How were fractals discovered? So, dating back to the 1600s, when Gottfried Leibniz discovered self-similarity, the idea of fractals began to build upon itself gradually throughout the following centuries. Self-similarity is when the quality or state of having an appearance or characteristic does not change as the object is made larger or smaller. So again, using this triangle example, we can see that where this big triangle has 3 of these medium-sized triangles in it, and then this medium-sized triangle has these 3 components in it as well. So it does not change no matter how big or small the scale is. The background of fractals. So Benoit B. Mandelbrot was the one who created the term fractal from the Latin word fractus. This was coined from the idea of the Latin definition, which typically meant like fractured or broken. And using this pattern of repetition, fractals became essential in mathematics as a concept could be applied to many real-world applications. So, how did this concept relate to math? The introduction to the fractal dimension, which can be described using fractional numbers instead of whole numbers. The fractal dimension is a method for characterizing fractal patterns by quantifying their complexity as a ratio of the change in detail to the change in scale. So, in simpler terms, this is more so describing how that no matter how complex or simple the shape is, it will still continue to just be a ratio, essentially, of the complexity and kind of how big or small the shape is. So, to kind of go further into that, we would use this fractal dimensional formula, which kind of explains that better. So our formula is d equals log of n divided by log of r, where d is that fractal dimension we'd calculate, and it is always going to be some type of ratio number. It's never going to be like a truly whole number. And our n is going to be the number of self-similar symmetrical copies of the original shape. So using this triangle, we can see if we were to calculate different parts of it, we would have different numbers of the self-symmetry. So we can see this big triangle is made up of 3 of these triangles, and then so forth, where if we keep zooming in, this triangle is made up of 3 more. So depending on what part you're trying to calculate, you can use, or you will have a different number of self-similar copies. And then our R will be the scaling factor applied to the shape when creating these copies. And once again, we can see this triangle is the same. The big triangle is divided into these more smaller triangles, and it has the same formula where it's one big triangle made up of 3 medium-sized triangles, and then it would be one big triangle made up of these 3 medium-sized triangles. So the scale would just be that R value. So the most popular fractal example that I'm sure maybe you might be aware of is called the Koch snowflake or the snowflake curve. So that is essentially when you would take an equilateral triangle and then you continue to add smaller equilateral triangles on it to create an infinite shape. And I believe it does look like a snowflake. That is why the example is called the snowflake curve. And so this will have a finite perimeter, or a finite area, but an infinite perimeter. And for this example, our n value would be 4, and our r value would be 3, and our d value would then be approximately 1.26. So how is this beneficial in real-world scenarios? So fractal-based algorithms are often used in video games for rendering landscapes to save storage. If anyone knows anything about kind of how certain games are. A lot of those open world games are very storage consumption based, just because they generally have a planned out landscape that they use to make the game, and that takes up a lot of the storage of the game because of the assets. So we can use fractal based algorithms to kind of minimize that amount. And we can also use fractals to hypothesize the distribution of galaxy clusters in the universe. Again, applying that same concept of how fractals are repetitive and they are like self-similar. We can kind of use that to infer where these galaxy clusters will be by using that pattern to see, once they expand far enough, how self-similar they will be in certain areas. An example of fractals in video games. So the popular exploration game Minecraft uses this type of technique for their world building. If any of you have played Minecraft or have heard of it, I'm sure you have seen at least the minimum, maybe a screenshot of the game where it's very block-based and it looks very different from one another depending on the type of biome it is in. So, in addition to using something called Perlin noise, Minecraft uses fractal noise, a customizable visual noise pattern that can be used to generate height maps for mountains. So, Minecraft specifically uses 3 fractal noise patterns, noise maps named the continentalness, erosion, and peaks and valleys to create the randomly generated and explorable biomes found in the game. So the continentalness is essentially the different type of biomes that you may see. In Minecraft, there are a lot of different types of biomes. So there can be a plains one, there can be a forest, there can be a snowy one. And so that's kind of that generative factor. The erosion one is essentially how flat the biome will be. So if you look at a plains biome in Minecraft, typically it is a more grassy area. It's flat. There is not very many mountainous areas. And so that, in comparison to more of the clay biome, which has a lot more peaks, it has a very different level erosion factor in comparison. And then the peaks and valleys fractal noise map is used to essentially create those different amounts of peaks and valleys in each of the biomes and everything to kind of fully build that world in the game. So here is a demonstration of drawing that simple fractal triangle shape that I was using as an example earlier. You can obviously do this by hand. However, the easiest way is if you do have some sort of digital altering technique to enhance that. Drawing it by hand can be done. However, it is a bit more complicated just because you have to remember kind of the pattern of doing this. But to start off, you can see I had this tiny triangle, which I then duplicated and added each of the smaller triangles to each of the sides of this shape, creating, a slightly bigger triangle. So for this pattern, what we're going to do is keep duplicating this initial shape or the initial shape and adding it onto the ends. So you will see in the video, I will duplicate this shape and then add the new triangle onto this side and this side. And that will be kind of the start of our fractal pattern. And as you'll see towards the end, it will get bigger and larger very quickly. So you can see here, I duplicate it, and then I will take that pattern and move it so the tip of the triangle is touching the very end of that other triangle, and then I will make it one big image, and then we'll follow that process. So we'll copy the triangle, and then we'll bring it so we bring the tip of it to the very edge on one side, and we'll do it to the very other. And as you can see, we already started to have that infinite pattern where there is one big triangle made up of these 3 smaller triangles, and then those triangles are then made up of smaller triangles. So the pattern can get big very quickly. There are other types of popular fractal patterns. I'm sure potentially you've heard of one called either the dragon pattern, which is more of a kind of spirally type pattern. It gets very extensive very quickly. This one, however, is the easiest, I think, to demonstrate that look of that fractal. So again, we can see it's already getting significantly bigger, and you can see the difference and how quickly it builds upon itself, as well as how already it looks identical and has that self-similarity. So this triangle is the same as this one, which is the same as this one. But then within these triangles, you can see they are similar. So as you can see, now we have this fractal pattern. And upon zooming in, we can see that it just continues that self-similarity until we get to the very small part. And then zooming out, again, we can see that self-similar pattern.